So bi-junction transistors, or BJT. Okay, and sometimes you call it bipolar transistors. I like the first one because it has, some very nice abbreviation, which is BJT. Okay, so let's decrease this a little bit. Okay. The main applications for the transistors are actually two applications. So the first one is as a switch, or more specifically electronic switch. So it's like, guys, a switch, button switch, you press, it's on. For example, if it's not pressed, then it's open. So this will be something similar to this push button switch, but electronically. So you can control it not by pushing, but you can control it using a signal. If you send some signal, okay, it will be closed, like it will be act like a pressed push button switch. If it's open, it will be, if the signal is with some other value, it will be off. So something like this. So if this is a push button switch, you need to press here. So pressed means short, not pressed it will be open. You can do that with transistors. So transistors can do something similar to this, but electronically. It will not be a press, it will be, using some signal value. For example, if the signal is 5 volt, if this voltage is 5 volt, it will be something like this. High signal, we can say. If the signal is low, for example, 0 volt, small signal or low signal, it will be open. Okay. The second most important application is amplifiers. Basically, if the input is something like this, the output will be bigger. Same shape, but bigger. So this is the output. Okay? So, and we're going to concentrate on the amplifiers in most of this chapter of the course. So, how the amplifier looks like? Amplifier circuit, I mean. It is something like this. You have some V input, some signal. Then we have the amplifier circuit, which is a black box till this moment. Of course, we're gonna dip into that and see how it will work. Here is Mr. V input. Here is Mr. V output. It should be equal to some constant larger than 1 or greater than 1 multiplied by V input. So for example, if K is equal to 2 and V input is, for example, sine omega t, just a very, irregular signal, V output will be 2 sine omega t. So if the V input is something like this, V output will be something doubled. Okay? Okay. So before going into transistors, I'm going to give you an idea how we can do this amplifier using some, common elements in circuit theory. And we can do that basically using voltage dependent current source. So we can construct an amplifier using voltage dependent current source. You guys are familiar with voltage dependent current source? Let's give it introduction. So this amplifier here will be something like this. A current source which is dependent on some voltage. So the current, let's call it I, equal to V or kV. Some constant, K is some constant, and V is some voltage. Here is V. So this is the amplifier. We're gonna see now how it can amplify a signal. And it have four terminals. Or two boards, each board has two terminals. So we have here these two boards, and we have here another two boards. Here is the input that we want to amplify, and here is the output. And let's have a load like this, okay? And here is the output along the load. Let's analyze this and see how this voltage dependent current source can really amplify a signal. So, good. So let's analyze it. So first, from this loop here, V is just equal to V input. So V input like this, V is like this. If you make Kirchhoff voltage law, V input minus V equal to 0, so V equal to V input. Based on that, I KV input. And now let's see what V output is equal to. So this I is flowing in that way. So the voltage across the resistor will be in that way, opposite to the current. So VRL equal to I RL, and I is equal to KV input RL. So VRL is equal to KRL V input. So from that small loop here, VO is actually minus VRL. So it's equal to minus KRL V input. So just forget about the sign now, the negative sign. Okay, we can live with it. Okay, if K, remember that this is a constant. So the resistor, have a constant value. When you buy a resistor, it's 500 ohms. It's 500 ohms. It's a constant. And the K from the beginning, we said it's a constant. Okay, it relates to this voltage dependent current source. So let's assume this constant is larger than 1, for example, equal to 5. So VO is equal to minus 5 V input. Again, neglect the sign. We can live with it. Okay, so what we have here as a magnitude VO is 5 times V input. So if V input something like this, VO will be 5 times larger. So 2, 3, 4, 5, very large. Two, 3, 4, 5. This is VO. Okay, and this is V input. This is the magnitude of VO. Okay, and again, we can live with the minus sign. We can have, we don't care much about the phase. This is called phase shift with 180, but forget about this. We can live with the negative sign. but what we really need is something, same signal, sine is again sine, but it's enlarged. And actually, in our context now, this V input might be a microphone. So V input might be a microphone, your mic that I'm talking to right now. Okay, and this RL might be, this is a particular example, might be the speaker, resistance. So it's the equivalent resistance of the speaker. So you can hear me, okay? And we can, if you guys can see, we can control the gain. This is called the gain. Using this, knob here, you can make it large or low, okay, based on your preference. This is a practical example. Now the problem is, if you're gonna go to electronics shop and you wanna buy a voltage dependent current source, they're gonna laugh at you. They don't know, or they may be not aware of this. So we need to make a circuit, which of course is a rule of transistors now, okay, that act as a voltage dependent current source. Turns out this can be done using transistors. Okay, so let's go deep now to the transistors and see their structure and symbol. Okay, so let's see the structure and symbol. Of the transistor. Okay, so this is the structure of the transistor. It's three regions. This region is N type. This region is P type, and this region is N type. This is called NPN transistor. Later we're gonna study another transistor called PNP. This will be P, this will be N doped, this will be P. Okay? So it has three terminals. One terminal here from this very thin region, and this terminal called base. So this is called the base. Let's do another color here, base. We have another terminal here and another terminal here. So till this moment, this is a symmetric device. I mean, this terminal is just equal to this because this is region is just like this region. Both are in. No. So this is actually not true. So basically, this region here will be heavily doped. Heavily doped. I mean, I will put more doping in that region than this region. And this region is called emitter. As we will see later, this is actually the source of our current. And this terminal is called collector. And we will see later that this region here collects the current that came from the emitter. Okay? So let's write this down as another color here. So this is the collector region. And this is the emitter region. And we have it the base region. Okay? And it is asymmetric structure. Okay? And here is the symbol for that guy, because in circuit we replace all these complex structures just like the Bi-junction with a symbol to make it easier to draw. So this is the symbol for the transistor, the NPN transistor. This is the collector, this is the base, this is the emitter, and usually we just write the first letters. Okay. Good. So let's have some observations about this structure. So we said that the base region must be very thin. Very thin. I mean this very thin or very small compared to other guys. Okay. Number two, the emitter region is heavily doped. Okay. If we look closer now, we have two BN junctions. So we have here a BN junction between the base and the emitter. So let's call it J1, junction 1. And we have another junction between B and N. This one here, J2. Okay? And since we are concentrating on amplification, okay, there are some requirements for J1 and J2 so that this transistor, this structure can work as a voltage dependent current source, so we can use it as an amplifier. Okay? So the two requirements are as follows. J1 must be forward biased. And J2 must be reverse biased. Good. So this should be forward, this should be reverse in order for that structure to work as an amplifier. Okay. Okay, so let's see the conditions now for that. Okay. So for the operation. So let's now check the operation. So another title here. Operation of BJT, of BJTs. And sometimes call them BJT, sometimes bi-junction transistor, sometimes bipolar. All these terms are the same stuff. Okay. So basically, just one note here: when G1 is forward and when G2 is reverse, this is required for amplification. And we said that with these conditions, we said that the transistor is in active region. Just because there are other regions that the transistor can work in. So let's see the operation of BJT. Okay, in active region, to be more specific. And before that, we need to revise or review two principles. So two principles before we go deep in that. Principle one: if you have a BN junction, like this, here is B, here is N, and the N region is heavily doped. So this is heavily doped. Okay. You remember, guys, we said that there are two currents. There are electron current and there are hole current. So if you have the N region is heavily doped than the B region, so you have more electrons crossing from N to B and less holes crossing from P to N. So IE will be much larger than I holes. Okay, this is the first principle. The second principle we have to before we go in the transistors is that, and here is the condition, of course, is forward bias. Again, if you have a BN junction, but now connected in reverse, and it's a normal one. I mean, there is no heavily doped regions. not like this one. And this one is connected as reverse. We know that there will be no current flowing, only the saturation current, which is very small. Okay, and you will have here, these positive ions, and you have here negative ions, and here is V reverse. What if somehow we inject electrons from here? So somehow we figure out to inject electrons from here, So what's gonna happen for these electrons? Okay, so you have here a battery, and the positive terminal is near the N because it's a reverse bias. Okay, so what really happens here when you inject electrons from that part, from the B part, okay, these electrons will be drifted in that way. They will move and they get consumed in the battery. So you will see current at that point, although it's a reverse bias junction, but this current came from outside. It's not from the junction itself. Okay, good. So let's apply these two principles to understand what's going to happen when we make G2 forward and G1 reverse. But before that, let's draw it again. We have here the base, okay, P. Here is the collector, and here is the emitter. I'm sorry, it's N also. So we want this junction to be G1, to be forward. So I'm going to connect to it directly a battery like this with VBE voltage between 700 to 800 millivolt, or between 0.7 to 0.8 volts. Okay? Between the base and the emitter. And we want this junction G2 to be reverse. Okay. Now, so J1 here will be forward for sure. Now for J2, we're going to make this the following. We're going to connect instead a battery between the collector and the emitter in that polarity. So we call it VCE because it's between collector and the emitter. Okay? But we want J2 to be reverse. So let's see what is the condition for J2 to be reverse. So we want the voltage between the base and the collector to be negative. So we want VCE to be less than or equal to 0. So in order for G2 to be reverse, VCE must be less than or equal to 0. Okay. So if we make a loop here, this bigger loop, we found that, did we change? No. That VCE is equal to VBE plus VCB, collector base. So VCB equal to VCE minus VBE, which should be less than or equal to 0. So VCE, do we get it right? So this should be positive to this, and this should be negative to this. Okay, VCB, I'm sorry, VCB larger than or equal to 0, I'm sorry. Yes. So we want this J2 to be reverse. Reverse means that the voltage of the collector must be larger than the voltage of the base. So we want the voltage of the collector to be more than the voltage of the base. Okay, so VCB should be larger than or equal to 0, not less than. So we're gonna fix that now. So it should be larger than or equal to 0. And here again, this should be larger than or equal to 0. Okay. So in order to achieve this, VCE should be larger than VB. So put any voltage here larger than VBE, this will make J2 as a reverse bias junction. Okay. Now let's apply the two principles that we saw in the last slide and see how this gonna operate. We said that the emitter is heavily doped, okay, and this junction is forward bias. And we said that if you have a junction forward bias and one of the N or B is heavily doped, it will have more current than the other. So we expect to see more current flowing from the emitter to the base rather than the holes flowing from the base to the emitter. So these are the holes, these are the emitter. So based on principle 1, IE will be much larger than I hole. This may be 1 to 100 or 1 to 100. So for each hole here, 200, for example, electrons moves from the N to B. Okay. And now the second question, where these electrons will go? And actually they will continue in that way. And this is based on principle 2. Okay, if we go back here, if we look at the principle 2, I don't know where it is. Yeah. So here in principle 2, if you can inject electrons into a B region in a reverse bias junction, these electrons will move to the positive terminal. So that's what we have here. So this is the kind of injections that I was talking about. So we could inject here some electrons into this, reverse bias junction. So most of these electrons will move to the positive terminal of VCE. So based on principle 2, IE will completely, or most of the electron will move to the collector terminal. So let's draw that in red. So most of these will just move toward the positive polarity of the battery here. Okay. And now let's ask ourselves a question. So there will be a current here called IC, although this junction is reverse. Okay, and this current actually it is actually the junction current. So IC is the junction J1 current. So IC should be dependent on the junction voltage. Which is VBE. And the answer is yes. There is a relation between IC, the current flowing in this loop here, and the voltage here VBE. And this is actually a diode, exponential relation like normal diodes. So actually IC is found out to be equal to IS, saturation current, exponential VBE over VT minus 1. Okay? So we are close now. We have a current. We could flow a current through what? Through a reverse bias, which is G2 junction. And this current is dependent on somewhere else. Okay? Now the question if it's a constant or not. Okay? So we have here another voltage. So now based on that, if we change VBE, IC will change. It's just like a diode. Okay? Now the question, if we change it VCE, remember you have two voltages, you have VBE and VCE. What's gonna happen to IC? If we look at the relation here, there is no relation between IC and the VCE. So it's changing VCE, but between brackets in active region, will not change IC, or IC is independent. IC is independent on VCE in active region, because in some other regions, we're gonna see this later, there are some dependency. So based on that, let's do the relations. The relation between IC and VBE. It will be something like this. Okay? And the relation between IC and VCE, it will be constant, something like this. Okay? So let's assume that IC, let's assume so, IC is equal to IC1 when VBE equal to VBE1. Whatever the values are. Okay? What happens if we increase VBE to some value called VBE2? So VBE2 is larger than VBE1. So IC will be IC2, and this IC should be larger than IC1. So, for example, if this is IC1 and we increase VBE, so IC will increase, so this will be IC2. How about if we decrease VBE to some value, VBE3, and VBE3 is less than VBE1? So IC will be some other value, IC3, which is less than IC1. So something like this. This is less than IC1 because VBE1 is larger than VBE3, and here is IC2 larger than IC1 because VBE2 is larger than VBE1. Okay, so let's now have a moment and look. Of course, there are some, it's incomplete curves because it's a constant line now, but it's incomplete because, as I said, there is another region called saturation region in which IC will change with VCE. But let's look at just the active region. In the active region, you will have some constant like this. I mean, whatever VCE changes, IC will be constant. So here, for example, IC, for example, 1, IC is 5. Here, VCE is 2. IC is again 5, and so on. Okay, something like this. And let's go back to our first demonstration of the amplifier. We said that the amplifier is a voltage-dependent current source, and we know from circuit theory, if you have an amplifier, if you have a current source like this, okay, for example, it's giving 5 amps, whatever the load that you are connecting, it will still giving you 5 amps. So if you connect with R equal to 1 ohm, the current flowing here will be 1 amps. If you connect it to 5 ohms, the current is still, I'm sorry, 5 amps. 5 amps. But the voltage will be changed. So the voltage here is equal to 5. The voltage here is equal to 25. So the current source provides the same current whatever the voltage difference around it. So here the voltage difference is 5. Here the voltage difference is 25. We have something very similar here. IC, if VBE is constant, IC will have some value, okay, in that branch here. Whatever the value of VCE, okay, if VCE is 5, IC whatever, for example 1. So let's say VBE at some point makes IC equal to 1 amperes. And VCE at that point was 1 volt. Then we increase VCE to 2 volts, but still VBE at some value, still the same value. So IC will also 1 amps. It will not change. So this is actually a voltage dependent current source, okay? So this is how, this of course, overview. It's not, of course, in-depth details of how, it's operating, but this is, a high-level overview of it. It's not, completely explains the situation, but very close to it, okay? One last thing to mention here. So this is, so the first conclusion is that we can build a circuit that can behave as a voltage dependent current source. This current is IC, the collector current, and it's dependent on VBE, okay? And if you see here, IC is here and VBE is here. It's based on somewhere else. And the second observation in here is that IC is actually just like a junction current. So it has exponential relation with VBE. Okay? So that's basically the two takeouts from this. Let's now go to another topic, which is the junction currents or terminal currents. Let's draw the structure again. This is the emitter, this is the collector, and this is the base, and this is VCE. So we said that this junction is forward, so most of the current flowing through the junction actually come from the emitter. That's why they call it emitter. And this collector current completes its way to the collector. So the collector will collect, these electrons. Okay, and we said that IE is much larger than IH. Okay, so if we look here, this IH is actually has a source. So it came from, of course, the holes in this region. Okay, and it's flowing actually in this terminal here. So the current goes into this base, it actually compensates this whole movement. So IH is actually equal to IB, or IB is equal to IH. And the IE is actually equal to IC. But there is some change here because the current should be opposite to the movement of the electrons. So the direction should be in that way. I'm sorry, it should be in that way. So the conventional current direction is opposite to the electron current direction, but the whole current direction is actually equal to the conventional current direction. Okay. So we have here two currents. We have IB and we have IC, which is IE. Okay, and both of them are combined here. So the resultant current here, IE, is actually equal to IB plus IC. And you can notice that easily from here. So the current here will be divided into sections. One is going that way, which is IC, and it continue like this, and one is IB, and it will continue like this. So IC equal to, I'm sorry, IE is that emitter current is equal to IC plus IB. So the first equation here is that IE equal to IC plus IB. Another observation, it was found that IC is proportional to IB. Whenever IB increases, because when IB increases, that means VBE is increasing. Okay, so another way to look at the relation between IC and the VBE is by looking between the relation between IC and IB. They are all the same. So IC proportional to IB, and they found that in active region, the relation will be just, between them just using a constant, like they call it beta. And beta is practically between 50 and 200. Can be 100, can be 150, whatever. Something between 50 and 200. And that means the current in here, IC, is much, much larger than the current IB. So IC is much, much larger than IB. So that sometimes they just equate IE to IC. Sometimes, not all the time. Okay? So these are the terminal currents. So let's summarize all the equations that we took so far. First, IC equal to IS exponential VBE over VT minus 1. IC equal to beta IB, and IE equal to IC plus IB. Sometimes they call it, they just substitute IC with beta IB, so beta plus 1 IB. And when you have very large beta, sometimes you just say IE is equal to IC. Okay. One last equation that I missed is as IS, the saturation current here. So IS is equal to, let me grab this equation here. You don't need to memorize it. Where is it? Yeah. So the area, just like the old IS that we studied in the diode, multiplied by the charge of the electron, Ni square, and the diffusivity, or Dn, the factor that determines the diffusion of the current, over the width of the base, multiplied by the doping of the base. So this is the doping of the base, width or thickness of the base. So this is W if we have the, yeah. So this is WB actually. Okay. Yeah, that's it. So this is IS. So again, here the observation is that IS is dependent on the area, just like what we have in the midterm exam. So if you double the area, the cross-section area of the transistors, IS will be doubled as well. Okay. So I'm gonna, publish a very small homework, just practical applications for this equation, just to train yourself about them. So let's have a small example. So we have a BJT transistor. with IC equal to 1 milliamps, IS equal to 10 to the power minus 16, beta is 50. Find VBE and IB. Okay, the solution. So just direct application of the equations that we took so far. So we know that IC equal to IS exponential VBE over VT minus 1. VT is equal to 26 millivolt. So from this, we have IC over IS plus 1 equal to exponential VBE over VT. From here, VBE is equal to VT ln IC plus IS plus 1. Okay? If you substitute, you will get VBE equal to 778 millivolt. And this was expectable, because we know that the junction usually have a voltage around 0.7. Okay? Beta is equal to 50, so we know that IB is equal to IC over beta. So IC is 1 milliamps divided by 50. This will give you 20 microamperes. This will give you also an idea about the values that you're going to see for IB. IB usually very, very small, okay, in microamps. Okay, basically because IC usually in milliamps. So when you divide by 100 and beta between 50 and 200, usually you get something in microns. Okay. Okay, that's good. This is just a direct application for the equations that we took so far. So, of course, we are not done with amplifiers yet. We're gonna deep more in the next lecture to see how this transistor, because still there is one step before you understand how the transistor can be applied as a voltage dependent current source and used as an amplifier. Okay, we have 5 minutes still, so I'm gonna go over what you're gonna see in the quiz. Okay. I'm sorry, the homework. So again, the homework, this homework is that I'm gonna publish on the light emitting diode will be of out of 20. So it's very big, mark. Just to cover, it will be very easy. And it will cover the two homeworks that you just, get very small grades in them. Okay, so let's go over that. So you remember, guys, the 7 segment. So example on light emitting diodes. Okay, so if you remember, guys, you have the 7 segment display, something like this. And each one of these segments are actually a light emitting diode with a resistor, and it has some connections to some source to provide with current and the biasing, because these LEDs should be forward biased to give you light. So if we said A, B, C, D, E, F, this would be G. Okay. So, and this as a circuit will be something like this. Okay. And another V input. That will be very boring because we have 7 of them. Let's make it very clear for you. So we have here 6, yeah, this is 7. Okay, so this is LED 1 or D1, D2, D3, D4, D5, D6, D7. Well, let's call them by the letters. I have more context. So DA, DB, C, D, E, F, G. Okay, RA, RB, RC, RD, RE, RF, RG. Okay, and all of them here is connected to 5 volt. So a source, a battery, okay, that will provide some current. This current will be divided by on these branches. Here V input A, V input B, V input C, V input D, E, F, G. Okay? So let's have an example on this. So it's assumed that to turn on any LED V input, any V input of them should be 0.2 volt. 0.2 volt. Okay? And when any LED of them is on and giving you light, VD on or VLED on is 1.7 volts. If you remember, guys, we said that light emitting diodes usually have high, operating voltage. Okay, it's not 0.7 like normal diodes. Okay, so let's see the question here. The first question is easy. Find R. You remember we have here, many 7 resistors. Or find R if the LED needs 10 milliamps to give light. Okay, so for any one of them to give light, there should be 0.2 here. Of course, we have here 5, and the current should be 5 amps, 5 milliamps. Here is R. Okay, and of course, when it gives you light, this is the symbol of the LED. I'm sorry. To give you light, VD will be on and it will be 1.7. So good. So let's analyze any of these branches. Any branch, when it gives light, it will be something like this. Any segment of these segments segment will be something like a circuit like this. Okay. So let's analyze this